Thank you for joining us on DeBakey CV today. I'm John Cooke, the chair of the Department of Cardiovascular Sciences here at Houston Methodist Research Institute. And I'm joined by Professor Mike Snyder from Stanford. He's the professor of genomics, chair of the genetics department there, and a leader in functional genomics, proteomics, and something that's now called personalized multiomics. We just heard a spectacular lecture, and we're going to get to that in a moment. Mike is going to tell us a little bit about what he's been doing. But first, Mike, welcome. Welcome to DeBakey CV.
Thanks for having me here.
Yeah, thank you for joining us.
Been a lot of fun so far.
Yeah. Well, you've had a remarkable career in genomics and proteomics, and now you're doing this really interesting stuff with multiomics that we're going to hear about in just a moment. But tell us how you got to be where you are today as a professor and chair of the genetics department at Stanford.
Well, I grew up in rural America, I guess, and just was very curious about how things work, and that took me on the journey I'm on. I'm a PhD. I'm not a medical doctor, but I think I've always liked looking at things from a systems level, trying to see the whole picture. And I think that's how we got into big data, started doing research in this area. People used to study genes one at a time. We started studying them all at once. Yeah. And now we try and study as many molecules, as much data as we can get to try and understand how biological systems work.
Yeah. Big data and health, this is going to change medicine. So you said you're a PhD, but what you're doing is going to change how we diagnose disease, how we manage patients, and how we change our own behavior to adapt to the information that you're giving us. So tell us, what is multiomics?
Yeah, so it's part of big data. So omics means it's the collection of things. So your genome is all your DNA, if you will. Your transcriptome is all your transcripts, so it's part RNA that comes from your genes. Proteome, things like that. So these are collections of molecules. And what's special about today's world is we can now measure all these things. So we can measure literally tens of thousands of molecules in your blood and your urine all over the place. And so that offers new opportunities to see how your whole molecular function and physiology is operating right now. So I do agree with you. I think big data and omics is going to change medicine.
That's amazing. I mean, today you said that in the study that you published in Nature Medicine this year in May, you said in that study you were getting billions of bits of information from each patient. Tell us how you did that.
Yeah, so what we're doing is following people over time. I think that's a key concept. Right now, medicine is typically done statically, meaning you go to a physician, they measure you, and they say, all right, this is what you look like. I think in the future, people are going to be getting measured over time, and people will use that information in a very meaningful fashion. And what you want to do is see, what does your health look like, how's it doing, and if it starts changing, you can catch that early. And so, and that we think will be very powerful. So the idea of longitudinal sampling, then I think also this deep sampling of people will let us get a much clearer picture, instead of like having a very low resolution picture, if you will, which is what happens now in medicine, in my opinion. We can get a much higher resolution picture of your health with all these new technologies. And some of it you'll get in the physician's office, some of it you'll get from these devices like smartwatches and wearables that you can now collect health information on a continuous basis. In the future, maybe we'll get this later, but I think medicine will become Amazonized, if that's a word, where a lot of the health information, not all, but a lot of it will be collected at home and you mail it in and get back the data that way.
Wow, so you can get this personal multiomics at home at some point.
I think so. That will be the plan, or at least get the samples collected at home so that you can actually get sampled much more frequently.
It's amazing, the tens of thousands of molecules you say, that we're looking at the genome, we're looking at the gene expression, the RNA, we're looking at the proteins that are being made, and the metabolites circulating in the blood, all of that, plus the sensors that you're using. Oh, I forgot the microbiome.
Right.
And all of that information, in your Nature Medicine paper, you were following in the 100+ people over a period of 2 to 8 years. And you found some really interesting things, unexpected associations. Tell us a little bit about the discoveries that you made.
Yeah, so by collecting these different kinds of data, you do learn things that are important for people's health. And no one technology found all these things. It was the combination together. The genome did turn out to be important. So by getting your DNA sequenced, we could make risk predictions in 12 cases and found one variant that was also important for people's drugs they were taking. So in one of those cases, we discovered someone was at risk for a heart disease, and it turns out they had a heart defect they didn't know about from their genome sequence. And another person was at risk for cancer, and they did a follow-up, and it turns out they had an early thyroid cancer that was caught. So the genome teased out a lot, imaging teased out other things. We saw someone with early lymphoma that we only saw. They were not symptomatic. In all these cases, they were not symptomatic. We saw there were changes either in their biochemical markers that suggested they might have a precancer, or with imaging, we saw an enlarged spleen in the case of the early lymphoma. So different technologies tease out different things. Two people even discovered they were diabetic who didn't know they were diabetic.
Wow.
Yeah.
And one of the things I thought was really interesting was that individual who developed lymphoma during your study, the diagnosis was made by imaging. But when you look back, because you had been following this person for a couple of years, you look back and you found something in the blood that went up before the clinical diagnosis of lymphoma was made, 6 months before.
Right.
Can you tell us about that factor?
Yeah, so I mean, it is a research study as well as, if you will, a clinically useful study to help manage people's health. But in the case you're describing, it was actually 9 months. We saw a particular molecule go up. It's something called a cytokine, which is an immune marker. And it went up starting about 9 months early. And so we're hopeful. We need to run a proper trial but to see whether it's an early marker for lymphoma that everyone could get screened for. That would be a lot easier than doing imaging, for example.
Wow. So multiomics is a way to get new insights into disease and maybe make the diagnosis earlier.
That's right, yeah. So we hope to be able, I think that's the power of this. We're profiling people when they're healthy, which is very different from the way most medicine's done today. Usually people get analyzed, they go to the doctor when they're sick. And so we're very reactive. And so the goal these days is to keep people healthy. And we think by making tons of measurements on people, we can see if something's not quite right. And if it looks not quite right, they can do follow-up tests and see whether there are early signs of disease long before they're symptomatic. And as you know, catching disease early, it can be managed better and then treated. If you catch disease late, in many cases, it's often too late, like metastatic cancer. It's cancer that's spread and it's often impossible to solve. So that's the name of the game, predict disease risk by making these measurements and catch disease early. Again, and I think that's going to transform healthcare, we hope.
Another fascinating thing that you showed us today was that the microbiome changed, the diversity of the microbiome changed before people got sick. Tell us, what does that mean?
Yeah, well, that was in these two cases where people became diabetic. So they actually gained weight, their microbiome diversity drops. So your microbiome is thought to be very important for your
microbiome or the bacteria in our gut.
Yeah, that's right. So you may not know, but you have anywhere from 2 to 10 times more microbes in and on you than are actually your own cells. So we're mostly microbiomes walking around here. And most of that's in your gut. It's very, very important for your health. It breaks down your food, digests it, so you can actually absorb the nutrients, and it makes essential vitamins like B12. All these vitamins that are just essential for your health are made by your microbiome. So your microbiome is a key part of your health, and it's very related to your metabolism. And so what happened in this case was these folks were actually, we discovered their microbiome was going off at the same time they were gaining weight, and they became diabetic all at the same time. So we think, again, your microbiome is very tied into your metabolism, and certainly then losing weight, and in this case, the folks also went on metformin, which is what used to treat type 2 diabetics, and that also helped.
Do you think it was the change in the microbiome, the change in the gut bacteria that was causing the disease, or is it the other way around?
Yeah, we don't know. It's an association for the moment, what's cause and what's effect. I think that's something people are working on, but they certainly work hand in hand. That's pretty clear. In a study I didn't tell you about, I'm actually type 2 diabetic. And it turns out we discovered that I became type 2 diabetic initially after a viral infection, and later it's a little less clear. It could be a viral infection. So initially I became diabetic, I got it under control, and it came back. It's really fascinating. In my case, we discovered it's associated with something called epigenetic changes. These are changes that where your DNA gets modified, and it actually got modified prior to my becoming diabetic. So in that case, it appears that it's pretty tightly associated with metabolic dysregulation, that somehow my epigenetic changes were somehow associating with my glucose dysregulation and led to my type 2 diabetes. So they're going hand in hand in that case. Yeah.
That's fascinating. And now that you know this, I obviously can take better care of your disease.
Right.
Yeah.
Yeah, my case is pretty unusual. I don't know if you want to hear about it, but it's
Sure.
Yeah. So most type 2 diabetics, when they become diabetic, they take metformin, and every problem solved. But in a few cases, 20% of people don't respond. So in my case, I was gradually becoming more and more diabetic. We could see my glucose levels go up, along with something called hemoglobin A1C, which is a marker for type 2 diabetes, kept going up, and was in diabetic range and still heading in the wrong direction. And I took metformin, and son of a gun, it turns out I didn't respond. I'm in this class that doesn't respond. And so in my case, I'm very unusual. I'm what's called insulin sensitive, meaning I respond to insulin fine. I make insulin just fine. So what's wrong with me? It turns out I don't release it from my pancreas. And we actually then did the right measurements and saw that was the case, that I was not releasing my insulin.
So knowing that, could you change the therapy?
Exactly. So it turns out then there's a drug that was recommended for me. It's called Prandin, that actually stimulates insulin secretion, and it works like a charm.
Oh, that's great.
So in that case, by knowing what was wrong with me, we could take the right drug, and so we call it precision diabetes. It's actually treating me precisely the way I need.
That's wonderful.
Yeah,
I'm glad to hear it.
And I think this is the kind of thing that should be done for everyone, right?
Yeah.
There's a lot of diabetics out there that, like me, many don't respond, and I think if we understand exactly what's going on, we could treat them better.
Could you show the audience the sensors that you have on?
Yeah, sure. So some people may know that I wear 8 or 9 of these devices every day. So I'm wearing 3 smartwatches right now. They measure all kinds of different things. They'll measure heart rate variability, steps, activity. One of them even measures my blood oxygen. This ring is not really a ring either. It's a sensor as well. It measures, along with one of the watches, measures your sleep. So they measure all kinds of different things. I wear a glucose monitor. I even have a radiation monitor, so you can see if you ever come across high energy radiation. I'm happy to report that Houston seems to be very low, Palo Alto level.
We're okay right here then.
Yeah, everything's good here. No, so there's all kinds of devices, and this one that's sitting in front of us, this is an exposometer. So this will measure all the biologicals, like allergens, things like that you're exposed to. But it also measures
what you're breathing in. This is what.
Yeah, so it's an air exposometer. It's sucking up air, and it's collecting the particulates, so things like pollen, things like that, on filters, and it's got a chemical absorbent as well. And so we can measure all the biologicals you're exposed to, as well as all the chemicals that you're exposed to as well. So most people have no idea what they're exposed to, either at home or work or anywhere. And this is actually this is our latest device.
That's incredible. So this thing is measuring, what pollen you're breathing in, or bacteria, and also what kind of small molecules, other like hydrocarbons and other things that are in the air.
Yes.
So if wearing this in Palo Alto versus wearing it in Houston, what kind would you see differences?
I'm sure we will. It turns out location is the number one factor affecting what you're exposed to. Season's a big factor though as well, what time of year. But location's probably number one. I don't know I have to measure this one when we get back home, so I don't know what the Houston exposure looks like. But I do know in Palo Alto there's DEET everywhere, the thing you use to keep insects off. There are carcinogens everywhere, but their levels will vary quite a bit. Some areas maybe not so great, and other areas there'll be very, very low levels. So, but we can measure all that, and the ultimate goal is to correlate it with your health. In my case, it's pretty curious. So I have very, very mild allergies. I always assumed they were pine because of when they appeared. It turns out they correlate better with eucalyptus. And in hindsight,
there's a lot of eucalyptus in Palo Alto.
There is, and I only seem to be allergic when I'm in California, where there's eucalyptus around, not so much on the East Coast. So in hindsight, I probably should have figured that out. But I could correlate that from this exposometer. So we think this information is going to be incredibly powerful for helping people better understand their health and manage it better.
Fantastic. I think this is just exemplary of what we want to do here at Houston Methodist. We want to take our basic research insights, like as you have, and then translate those into something that's useful for people. So
Right.
Today you gave the inaugural presidential seminar lecture, and it was you were the right person to start with. Thank you so much for visiting us, Mike.
Thanks for having me here.
Keep
Yes.
up the spectacular work.
Well, I look forward to working with you guys.
And
more in
let
the
us
future.
let us know what was in the filter.
Absolutely. If there's anything nasty, you'll be the first to know.
All right.
You'll be the first to know regardless. Anyway, very good, John. Thanks so much.
Thank you, Mike, and thank you for joining us today at DeBakey CV to hear from Mike Snyder, professor of genetics, the genetics department, is chair there at Stanford University. Thank you.